I would like to present here research about method of coaxial accelerometers correlation for quality assessment of structural joints. The great amount of buildings is exploited now, and most of them have the big problems with the joints. The question is especially actual for the buildings erected in the big series 40-60 years ago. Assessment of the joint stiffness is important for its design, monitoring of the condition of the building structures, and prognosis of the lifetime and safety of buildings or its elements. Application of the destructive test usually is not possible, and such assessment is done by a non-destructive way using either shock or vibration analysis with a network of accelerometers as sensors. The suggested method of Coaxial Accelerometers correlations is based on the natural accelerations. The aim of the current study is to develop a method which is based on the natural oscillations for quality assessment of the structural joints. The method should be based on the mathematical analysis of natural vibrations of structural joints in 3D spatial directions using 3D accelerometers located at different parts of joint and oriented coaxially. The stand of timber beams with the moment joint with variable stiffness was tested to check the suggested method for quality assessment of structural joints. The stand of timber beams consists of the main and additional beam made of C18 strange glass solid timber. Statical schemes of main beam was freely supported beam with the span of 2 meters, and for additional beam it was 2 spans continuous beam with 2 spans of 1.5 meters each. The beams were joined by the rigid joint and statically loaded by the system of vertical concentrated forces with the total intensity from 1 to 10 kilonewtons to specify the statical scheme of the beam's stand and type of the beam's joint. The statical scheme of the beam's stand depends on the stiffness of the beam's joint, which was varied during the experiment by adding or removing the screws used as the fasteners. 6 deflectometers and 6 strain measuring devices were used in course of statical test to verify the statical scheme of the beam stand. The beam stand also was modeled and analyzed it by the finite element method. Three statical schemes of the timber beams stand were considered with different types of joints of main and additional beams. Rigid, pinned, and free joints were used to consider probable stages of the joint's degradation and were obtained by the removing of the separate fasteners, screws, and joining steel plates. The joint stiffness was determined basing on the experimentally obtained angle of the joint's rotation. The experimental obtained values were compared with the values obtained by finite element method also. Joint rotation angle as a function of the applied vertical load are shown on the figures for symmetrical and non-symmetrical loadings. The maximum rotation angle was obtained in the case with non-symmetrical loading. The joint rotation angle of pinned joint at the maximal loading is 10 times larger than for the rigid joint. So the task of the statical loading was obtained, and it was studied that considered variant of the main and additional beams joints can be considered as the rigid and pinned ones. Dynamic test of the beam's stand was carried out to check the suggested method for determination of stiffness of considered before rigid joint. The additional beam was subjected to a vibration load provided by the electrodynamic actuators fixed on the edge of the additional beam. Vibration in the different parts of the joints was fixed by the using of 3D accelerometers joined with the computer. To improve the quality of diagnostics of structural joints and to make it more specific, a method and measurement system realizing the principle of correlation of normalized coaxial accelerations measured in 3D space were proposed. Algorithm of the method using contains the following stages. The first step is a sound signal with the maximum wide frequency spectrum is applied to the tested structure. Then obtained vibration record is analyzed by the Fourier and effective frequency spectrum where measurements by the vibrometers are maximum is selected. New sound signals in the determined frequency spectrum are applied. The 5 measurements were fixed and saved. Stiffness of the joint is changed by the removing of some fasteners, and stage number 4 should be repeated. Experiment can be continued till the moment when stiffness of the joint will decrease till 0 level. Vibration record, electrodynamic actuator, and audio card are shown on the figures. Dynamic test was carried out for 7 cases of considered joint. Case number 1, rigid joint, then cases from 2 to 5 was rigid joint with a decreased stiffness, pin joint case number 6, and absence of the joint between the main and additional beam case number 7. Each of accelerometers take up vibration records in 6 directions, which are shown on figure. Both 3D accelerometers are numbered. Accelerometer number 1 was placed on the main beam and accelerometer number 2 was placed on the additional beam. The differences in the vibration records were reached in 3 directions. But the best results were obtained in the direction 4-5. Sigue software is used for analysis of obtained vibration records. Fourier transform of the vibration records obtained in the one direction 4-5 is shown on the slide. Comparison of transformed vibration records obtained by the both 3D accelerometers was carried out by the using all the methods shown on the slide. The best results show the peaks analysis of signal sum, which graphs is shown on the figure for the single measurements. Peaks analysis of signal sum obtained for the 5 measurements for the 7 cases of the joint are shown on the figure. Average values and its approximation by the power function are shown also on the slide. Stiffness of the considered joint for its 7 cases were analyzed by Eurocode and shown by the blue line of the graph. It was shown that the stiffness for considered cases decreases linearly, but the peak values of signal sum change not linearly. This line is shown by the orange color. Changes of the rotation stiffness for all 7 cases of the joint, so as changes of peaks values of signal sums, are shown on the slide. Peak values of the cross-correlation function between the responses from the correspondingly rotated pairs of coaxial accelerometers were determined. It was shown that the difference between the peak values of the correlation functions obtained for the rigid, semi-rigid, and hinge joints enabled specification of the joint stiffness. As a result, it can be concluded that a method of coaxial accelerometers, the correlation, which is based on the natural oscillations for quality assessment of structural joints, was developed. The method is based on the mathematical analysis of natural vibrations of structural joints in 3D spatial directions using 3D accelerometers located at different parts of joint and orientated coaxially. The method enables to evaluate the changes of the structural joint stiffness caused by its damages in process of exploitation. Thank you for your attention.